So study we started to get towards tree width, and we proved we reached we defined two important notions yesterday. And what was one is that let G be a graph and S be a subset of vertices, then S is called balance separator if all connected component of G minus S has size at most half of the original vertices. Okay, and we also saw that every tree has a balance separator of size 1. And using this, we saw an algorithm for maximum independent set on trees, which was just nothing but basically we said let's find a balance separator, then every component has size at most n over 2. Let's partition these components into A and B such that size of A is at least 1/3, size of B is also at least 1/3, and this is at least 2/3. Then the algorithm is that on this vertex I had two choices, either vertex V goes into the solution or vertex V does not go into the solution. Then the recurrence is T of n is roughly, if V goes into the solution then none of its neighbors can go into the solution, and then we said okay fine, then it is T of roughly n over 3 plus T of 2n over 3, and in the other case also when V does not go into the solution you delete it, and then you have, then I can make the component of size of this kind. And so we said this is very crude approximation, this was, and we saw that this is polynomial. Okay. So we wanted to repeat, and we also saw a linear time algorithm for this on trees. So we wanted to repeat this success, and to repeat this success we defined the notion of T decomposable graph. So what was a T decomposable graph? Okay. So notice that we observed we observed that if we want to do recursively some algorithm, then the connected component also should have that property, that I should be able to find a notion balance separator there, and hence we define, like, so in some sense this balancedness should be a hereditary property for its induced subgraph, and that is precisely what we captured in this definition of T decomposable graph. And what did we say? A graph G is T decomposable if for every W subset of Vg the induced graph GW has a balance separator of size at most T. And then we define Zt equal to G, G is a T decomposable graph, and G1 was like subset of trees. And now I asked you a question, suppose if I gave you this, and I also gave you a T decomposable graph, and I gave you an algorithm which can return you a balance separator. So you have an access to two things. Okay, you have an access to an algorithm, and we will see in a minute how can we get this access to an algorithm that can find balance separator, that can find a balanced separator of size T for now. Size T. And what is my goal? My goal is to still find maximum independent set. Okay. So what can I do about this? I just mimic this algorithm, right? Now what do I know? I know that okay fine, I find a set S, cardinality of S is less than or equal to T, and then each connected component has size, right, n1, n2, nl, and each ni is at most n over 2. We know by the definition of T decomposability, right. So just by the properties of here we could arrange them into A and B, I could also arrange them into some of them as A and some of them as B, such that their sizes are still some fraction of this. Okay. But now the problem is on S, I don't know which subset of my solution, I need to find which subset of these vertices go into my solution. So if I write a recurrence for maximum independent set, so what it will write? So maximum independent set of G is going to be max X subset of S, X independent set, right, X subset of S, X independent set, okay, MIS, okay. Now I have decided to pick X into my independent. So n of x cannot go into my subset, right? So then I find MIS of A minus n of s plus MIS of B minus n of s. This is how I would like to do it, and this is what I would like to return. Now I need to show why this is correct, right? To show it is correct, all I need to show that LHS is less than equal to RHS and LHS is greater than equal to RHS. Okay, this is what I need to show. Okay, fine. Look at any maximum independent set of G, right? Look at any maximum independent set of G. So that maximum independent set of G is going to pick up some vertex from here, 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 right? Let's try to understand this. So there is X subset of S which I am considering here, right? So look at what all maximum independent set this side is considering, right? So in particular the maximum independent set this side is going to consider is the one which maximizes my, so let's call this set as X. So I am going over that X, so let's fix that X, okay. Now look at A minus n of S. A minus n of S clearly doesn't contain all this, like its neighbor, because now I have decided to contain. That's perfectly valid, because if you contain X, you cannot, it should be n of X, right? You cannot contain A of n minus X, right? That's perfectly fine, because all I am trying to tell you that this independent set is realizable here. Now look at A side, it's a connected, disjoint connected component. So this independent set, this independent set, this independent set, this independent set is also an independent set of A minus n of X, right? But there could be much bigger independent set here, I don't know, right? So I am taking maximization over independent sets of A in which I have put it my own independent set. So this quantity can only be larger, great. Similarly with B. So what does that shows? That max independent set of G is less than equal to whatever quantity this computes, because whatever independent set I have in mind will definitely be considered by this recurrence in one go, right? But maybe there are other things which could be considered, and again we use the fact. Now let's go to the reverse direction, okay. Now when I go to the reverse direction, okay, fine. So look at the set X prime which maximizes this. Look at X prime for which this quantity is maximized, right? This is maximum. So this is some X prime for which this quantity is maximized. Look at that independent set. So that independent set consists of X prime from here, some I1 from A, some say IA from this independent set, IB from the independent set, because this is what, look at IA, IB, right, and X prime. So it should be, actually there should be mod X plus this, okay, this is what it is, because we also have to compute this, or yeah, just put it this, okay, doesn't matter. Now look at this, the object which maximizes this. I have to show this is an independent set of G, then I am happy, because this quantity is maximizing over all independent set of G. So in particular it will consider this, so this can only be larger, okay. Now look at X prime is here, but by choice neighborhood X prime is never considered. So clearly X prime is independent from IA, X prime is independent from IB, because by construction. Now look at IA union IB, because they were connected components, there are no edges going across between them, so this is independent set, and hence I am happy, right. Again I use the fact that they are separators, this separates and these are component. So the point is, for anything you must show this, okay, and I will come to your optimal substructure property today, okay, and why that's not a right way, like that's a archaic way of thinking things. Okay, okay. So do you agree this recurrence is completely correct? All I need to make sure is that I come up with an algorithm which implements this recurrence, right? So all I am doing now, fine, right? So what I am going to do, excellent. So I just, what will I do? So now I can run my while loop. So I guess the subsets of this, And then I run this algorithm, right? I could write a recurrence algorithm, recursive algorithm MISJ, which for all I subset, for all x prime subset of S does this, calls this and outputs the one with the min maximum size. So I can actually make this as a subroutine, right? But what is the running time of this subroutine? So look, first of all, T of n, what does it does? First of all, it finds a separator S. Suppose it finds in polynomial of time, like some time, some, say you have a constant, in constant time we found this, okay? We'll worry about this. Plus, given this, what do? I go over every partition of S. So every partition of S. So 2 to the power t, right? Because there are that many choices of S, right? Look at this, X subset of X, X is an independent set. I am just writing down whatever I have written here. Now, what is the size of this A minus X? So as I told you yesterday, you have to write max alpha is between 1/3 and 2/3, right? T of alpha n, right? This is size of A plus size of B, right? And plus order 1. Okay, this is what the running time of this algorithm is, nothing more than that, right? So, and you can show that this is worst when it is T of alpha n plus T of 1 minus T of n third, 2/3 when they are mostly imbalanced plus order 1, because I just find once, right, and then I go over all this. I am not finding this separator several times. And if you work hard, this will solve to n to the power big O of t, right? Why? Because basically it's going 2 power t is going to be repeated log n times. So this, yeah, 2 to the, so it will get 2 power t log n and you will get some n to the power big O of t, okay? Check this out. So the running time of this algorithm, given an access to that algorithm, its running time is n to the power big O of t. Now, if my running time is n to the power big O of t, do I need this access to algorithm that can find a balanced separator of size t? I can check all subsets of size t and check whether they form a balanced separator or not. So then I can replace this in n to the power big O of t time, and this still will be some n to the power big O of time. So in fact, this will be some n to the power t plus 1, just to be precise, right? How? Try all subset of size t. This is my algorithm, right? So I check, delete it and look at all the connected component and check their sizes. If all the connected component size at most n/2, this is a balanced separator. And since this graph is T decomposable, I am guaranteed that such a set S will always exist, okay? What, yeah, this just goes out. What do you mean they are not part of the recurrence? Of course it will come when I will go n/3. For that also I have to find a recurrence, find a balanced separator, right? Huh? There are more to the world than, okay, fine. So then, but if you put this, she says you will get n to the power t log n. Log? Yeah, so this is why. So if I use this algorithm, then I will have this, right? Still fine. Anyway, it should just come out to be n to the power. That is not my, great. So two questions, right? A, this is not, this is poly time for fixed t. And if I want to make FPT, I need to do something. First of all, I need an FPT algorithm here, right? Because this algorithm is not going to, if I, when I mean by FPT, like f of t into n to the power c if I wanted, right? Then at least this divide and conquer is not going to work. Okay. But if you notice yesterday whenever we were doing over trees, if you notice we had linear time algorithm using DP, right, and we had not linear time algorithm maybe n cube using divide and conquer. So now a natural question is, how can I organize, how can I do DP, how can I organize my graph that I can do dynamic programming which will compute this value? You get my question? How do I look, how do I do then? Look, when I gave you tree, you know how to do DP from left to right, bottom, top, right? I just have a graph which is T decomposable. That's all that is given to me. The question is, can I do DP by organizing my graph in some form or some way? Okay, right? I need to organize my graph in some form or way. Okay, and I have to also do many more things, right? I have to do dynamic programming. So I have to maintain suboptimal structures or whatever it is called. But if you think from that perspective, you are going to make your life very hard and miserable. Okay. So how many of you know if I give you a DAG and ask you to find some shortest path? Do you know how to find? I gave you a DAG, and I, okay. DAG, shortest path. I want to do dynamic programming, not interested in DFS, BFS. Okay. So what he's suggesting us to do, suppose we have V1 to Vn, which is a topological ordering. Okay. So what is the property of topological ordering? So every arc, uh, goes from small index to higher index. Agreed? Excellent. Okay. Fine. So what should I do now? Suppose I give you some vertex S. I want to find shortest path from S to everybody else for now. And suppose, okay, for making your life easy, suppose S is V1. Suppose they are weighted. Every arc has weight, and I want to find min weight. So tell me, like, So what should I store? Like what is my storing object? What should I store? So what is A of Vi is?
Min shortest path from S to
Min weight path from V1 to Vi or S to Vi. Okay, fine. So yeah, so what is the recurrence?
so whether VI is there or VI is not there. So in the case where VI
Can Vi not be there?
VI has to be there for me. So it will be like max of over all like you take all the neighbors and you add, so it will be
So what should I write?
min of over all neighbors.
What neighbors?
Like it has a forward out too. So if it's like there from
So what should I
VJ to
write?
VI,
What should I write? Tell me.
VJ to VI, min over all VJ to VI.
Okay, UVI.
Yeah, UVI. Now
Okay.
it will be like A of U,
A of
A of U
okay,
plus weight of UVI.
not weight of path.
Sorry, weight of H.
Okay. Is this correct?
And finally, what we do is we find min over.
No, I just wanted like min weight path from S to every other vertex, so it stores. But why is it correct?
Wait, so what is U again? U is the name or the name?
In neighbors. Okay. Min over. Okay. So all the suppose your Vi. Look at all these guys. Sorry, other way.
Again, you need to show this less than.
Yes. So if you show, that's correct. And if I wanted to find max path, I would have just used max. If I wanted to have a sum of these paths, then I would have done some sum. If I wanted some product, but that is not the point. The point is, what is this ordering giving you? No, it gives you a way to process your problem. And when you are processing, all the sub problems on which it depends, I have already processed. That's all that it tells you. So for any dynamic programming algorithm, there is a DAG associated with it. When you are going to consider a sub problem, all the sub which defines this sub problem is already been considered. There is like, so every dynamic programming algorithm has an implicitly associated DAG over which you are computing. Try your longest common subsequence, try your edit distance, and there is a DAG associated to it. Otherwise, you cannot do it.
So you're telling all these states can be associated with that.
I don't know what you mean by state, first of all. I know it's sub problems, right? So when I write my recurrence, when can I write recurrence? I can write recurrence in terms of something smaller. Either I can think of them as the sub problem optimal structure, I don't know what those words are, but, or I could just think, can I build something inductively with something smaller, right? A. B, if I build this, is there a way in which I can build them so that there are no dependencies which I cannot build them, right? So I need both these properties. So first of all, so whenever you write dynamic programming, you write recurrences, which basically means when you write recurrences, I'm able to construct this with some smaller objects. That's first thing. And secondly, I need a way to, what is that called? To process this object. And I should process this object in a way where all the things which I depend on has already pre-computed, which is nothing but I must have a topology. be some DAG associated with it, and I must keep that in mind. Okay, so the reason why I brought this up, because now that I'm going to do a dynamic, I'm trying to build, I made a divide and conquer algorithm which gave us a very good algorithm for maximum independent set, that is polynomial time for every fixed t. So this T decomposable graph is amazing object, because so there are lots of things. How do I identify whether a graph is T decomposable or not? I mean, that's not obvious. Okay, that's not obvious. And even if I gave you a graph, how do you find this balance? So, but what I would like at this point of time is to take this T decomposable graph and try to organize this graph in some way such that it is easier for us to do DP. Like, so whenever we were doing a DP yesterday over trees, how are we doing over, what is it called, some pre-ordered transversal, or what is it called, post-ordered transversal? Like what? When you were looking at a node, you had already had processed all its children. So what is this called? Post-ordered transversal. Yeah, and that already gives you a DAG, right? Because that the way you are processing, whatever you are processing, everybody. So now this guy depends on the sub. So if you think of, you write your sub problems and you give an arc, if this sub problem depends on some previous sub, this must be forming a DAG. And if you just draw that, whatever we did, that forms that. So I need to have certain association of this nature even here, right? Otherwise I cannot hope to do a dynamic programming algorithm. Okay, so we'll get to those things a little bit later. But if this is how it is, how did we, I mean, like what is the most natural way of, so think of this way, that I would like to do a post order transversal on trees. Okay, so given this graph G, given a graph this G, want to associate a tree T that allows us to do DP. And how will we do DP on this tree? We know how to do DP over tree, right? Go from leaf to root for any problem, like that gives us a DAG on which I should be doing the working. So if I associate a tree T, right, and I am doing DP the way do from bottom up, that already takes care of that I have a topological ordering, and where everything which I need to process at this node and which it depends has already been previously taken care of. So by associating this tree T, I have taken care of all this. Now this tree is useless because it's just a tree. Now we need to associate something from this graph to this tree that we start to have some meaningful conversation. Okay, so what should I do? I mean, here's our, if I would have been in your place, here would have been my first approach. So I have a graph G. What is, it's a T decomposable graph, so it has a balance separator. Excellent. Here is a connected component, connected component, connected component. Okay. Fine. This is also T decomposable, right? And have a strictly smaller vertices than this. So I could think of this. Okay, fine. I make a vertex V for this. I get a tree for this guy. I get a tree for this guy. I get a tree, whatever that means. So suppose I have component C1, C2, CL. I get a component, I get some association with tree T1, T2, TL. So this is a tree, this is a tree. And what I do, I look at the root, and suppose this is a rooted tree. Not only any tree, it's a rooted tree, right? It gives me, returns me rooted tree. Okay. Now what I do, I make another root R, make him children of, and make him adjacent to all this guy, right? And to R, I associate this S. Okay. So now what am I doing? I am trying to give a function from vertex set of trees to the vertex set of graph, right? I am associating something, and what I am associating at this point of time, I am associating the separators, right? I find a separator S, balances, C1, C2, CL. I said, okay, fine, give me a pair. So what will it return me? It will return me a function Fi, comma, tree Ti rooted. And what this function will tell? Look at this vertex set of this graph and associate such a function, right? So this is what the property of these functions are. So maybe I should not write Ti if I should write Ti Fi, and every tree is rooted. So I also get a root some Ri. So once you have given me this, okay, I can come up with a function for the whole graph. How? I will make a tree T, which I will make one root R. Look at T1, which is rooted at R1. Look at tree T2, which is rooted at R2. Look at the tree TL, which is rooted at RL. Make him adjacent. Okay, so this is my first attempt. And what is my function? Okay, my function is, now I have only added this vertex V, right? So f of Vt is, now this is the tree 2 to the power Vg, right, a subset. So f of R I associate S, and for any other, for any t, f of for any other V, f of V is some Fi of V, because they are uniquely in some tree. So I just concatenated these functions and then did this. Okay, so this is my first attempt. I have decomposed my graph, I have a tree associated with it, and I have a bag associated with it. Okay, now, so what did we do last time? If you notice, when you had tree and we were doing dynamic, right? Okay, we will see. I mean, we are far away from what we want, but isn't this the most naive way of doing this? And we'll try to fix this. Okay, so now what I try to do, okay, so now I have a graph and I have a tree associated with it. Okay, so I have a graph. So given a graph, I have associated a function, sorry, a tree and a function. I have associated. Now, okay, so when we were doing DP over trees, we had tree and we had a vertex V, and what we were saying, what was TV? Tree rooted at V. V. And what were we storing? We were storing some AV, BB or whatever, right? Maximum independent set in TV, max independent set in TV that does not contain V, right? Maximum independent set in TV, that this is exactly what we did. So basically at every vertex in the tree, we had some portion of my tree which was associated. But now given, suppose this is a tree now. Now what is TV? I mean, this is not the graph which we are interested in, right? So we need to associate some portion of graph to this tree. So what's the natural way of associating a portion of graph to this vertex? Well, that's very canonical. I mean, if you really think, it's very canonical. So what will I do? What is a GV associated at TV is equal to union over, so I associate, okay, W descendant of V, TV, descendant of V in TV, f of W. That's it. So this is a vertex sets, right? I look at the graph induced on them, right? That's it. So this is my association, right? Okay, so I can think of TV in the beginning, like for my trees, this function is its associate V to V itself. That's it, because it was a tree, so I didn't. But now, because I said, okay, fine, what graph do I consider? So the graph which I'm going to consider is, look at the subset of objects which I have associated, look at the union of these things. Agreed? Huh? V is also descendant of itself, no? Aren't you descendant of yourself? Okay, okay, fine, and V. Okay. So clearly, if I look at the first vertex, the G of R is the whole graph, because, and there is something more funky about this function. In fact, this function is a partition of vertex sets. Partition of vertex sets. Okay. So this is my first attempt of defining given a graph, I want to associate a tree, with this I have associated a graph, okay, and now I want to do dynamic programming algorithm. Okay. Now I want to do dynamic programming algorithm over this tree. I want to mimic my divide and conquer algorithm to this, and then we will see why this is a horrible approximation to what we are trying to achieve. Okay, and then we will fix it. Okay. So, if you look at picture wise, what is happening? So, if you look at this child, basically the graph which is associated to this child will be this connected component. The graph which will be, so look at the root and look at V1, look at R1, R2, RL, like here. So, if I started with this, then what is the graph which is associated to R1? It's basically the connected component C1. What is the graph associated to R2? Is a connect, because what did you do? You called yourself on this, so it can only contain vertices of this. Similarly here, similarly here, similarly here. Okay, excellent. So, what is the property? One great property which we were using in this independent set is that, hey, look at an object here, look at an object here, find an independent set here, find an, we can take its union. I can still do it because this is a connected component, this is a connected, so there is no edges going across. So, this property is amazingly satisfied, so I can still do all this thing, okay, but let us see what happens. Okay. So, I would like to do the recurrence. So, what will we do? So, now for all x subset of fv, so we have fixed a vertex v. So, x subset of fv means a some set of vertices which are associated, and what we want, what do a of x I want? I want maximum independent set in GV whose intersection with x, whose intersection with fv is exactly equal to x. It only picks x, nothing more, nothing less. This is what my meaning is. Now, so what will be then update function? Right? So, how will I write a of x? If a of x, clearly its neighbors cannot go into the solution. Okay. So, maybe I should write, right. So, maybe I should write here, this is not the right way. So, maybe I should write a v comma x. So, it tells us which node we are working with and which. Okay. So, now a v of x should be what? Summation over, right, vi is the children of v, and what should I store here? A vi comma, ideally I would like to write fvi minus neighborhood of x, right, because if I have decided to pick x, I cannot pick a neighborhood of x, right, and this is what we were doing in DP. Right? Is that sounds okay? We have to prove it, right, and then figure out why it's wrong or right. But this is exactly what we were doing for DP, no? Right? We decided to delete x, and from each of this connected component, we just ran the algorithm without its neighborhood, and that is perfectly correct. I am just trying to mimic that algorithm, and I want to understand why this is correct or this is not correct. Okay, so why this is not correct? Clearly, right, that is going to be independent. What is this storing? It is going to store an independent set, right? What is this guy storing? An independent set Vi at V, like look at the graph induced on Vi, it is going to store an independent set which doesn't contain the neighbors of X. So clearly that guy is an independent set here, 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 right? But now let's look at the other side. I took an independent set, okay, I found an independent set here, I found an independent set here, independent set here, independent set here, okay, and I would like to add X to it. Can I add like this? Inside? No, that we will assume that X is independent set for, otherwise you just say no. If X itself is not independent set, you cannot, so I can just put that 0, like infinity or something. What's wrong here?
Definition is whose intersection with FA is exactly. Here we are asking that it has to be f of Vi minus Nx. That need not be an independent set. But typically what definition that we want is maximum independent set of with X. So we don't want that intersection to be stored. So we want all subsets, but we don't want that exactly this subset.
I didn't get your point.
So what I'm telling is, here what will happen is, by the definition of A of Vx, we are asking for max independent set in G of Vi,
Yes.
whose intersection is exactly.
But X and this is here. If these vertices are not even here, so they will, those kind of independent sets will never be considered. Look, it's a partition of vertex set, right? So I decided not to pick these guys in the independent set. I mean, these guys cannot pick those guys because those vertices do not even appear here.
What I am telling is, if you look at this inside the summation, we have that, right?
Yes.
So what that is asking us is, do we have an independent set with max independent set in G of Vi, which has exactly this f of Vi minus Nx intersection? So, but that need not be.
Okay, so let's make with f of b subset of X, doesn't matter for me, okay. GV which is whose intersection with FB is contained inside X. Now does it make sense? Clearly I cannot get n of X, right? So it can only be contained inside f of b. So now does it make sense? If I just did this change? And I can also still compute independent set with this recurrence. Now it is correct, right?
Don't you have taken maximum over all the X? Specific X.
I am only storing for a specific X, no?
If you have to find
Look, when I have to find a maximum independent set of my graph, I will go through all X and choose the one with which maximizes the object. So at this point I am only interested in that maximum independent set which has this specific property. So this is fine. This is fine. Excellent. This is all. No, it's not. It's absolutely not fine. It's just wrong. Okay. What is it tells you? It is going to give me an independent set. Okay. Do you have any idea what is f of Vi is? F of, look at this. Let's look at this, right? So you have some association, here you use X. Now look at, just like let's draw 3 connected component. Okay? I have some root and I have association of some vertices here. This is what is, say, f of R1 is, f of R2 is, say f of R3 is. right, some association. And what is this telling you? Give me an independent set here which is contained inside neighbors of x which is not present here. This is all that it is saying you. How do I know that all the neighbors of x are present here? Who guarantees you this? Maybe neighbors of x, look at what this tells you. F of vi is this subset, but x could have neighbors here. Now when I look at the independent set which does not contain this, because this is what I wrote here, right, then I can contain some guy here and some independent set here who could be neighbor to x. I have absolutely no control over what f of Ri is storing, right. So if I locally am going to optimize that, it very well could contain a vertex from neighborhood of x. All I am saying that he has not, this independent set does not contain neighbor of x that is contained inside this little bag, this little bag, this little bag. That is all that it is saying. It never tells me that it will not contain a neighbor of x which is outside these little bags, because I have absolutely no control over how these bags are. So at least this way of doing things is not going to work out. And why did this not work out? Look at your edges. There are lots of edges your graph did not even bother to consider. Did your graph even bother to consider edges between S and this component? No, it forgot. When he considered this, he actually forgot all the edges, the connection between S and him, connection between him. When only time when I consider this, but when I am going below, I should have some record of information how this guy is interacting with this, and that information I am just not storing at all. So why do I expect that my algorithm is going to work completely independently as this? So this is a right approach to make a decomposition, an association, but this is not going to work. So we need to fix this. How are we going to fix this? Okay, fine. So what's a natural way of fixing this? A natural way of fixing this will be fine. Okay, good. Okay, so you guys are creating a lot of mayhem. So let's, here is a C1, C2, CL. Let's enrich Ci tilde and I look at this graph. Okay, and what is C2 tilde? I will look at this graph. Now I am storing the association which I have, right? And what I do as C3 tilde is this, okay? And now I want to come up with these things. So now what I will do, fine, great, okay. So what will I do? I mean, all I need to do is some association of this. So I still start. I said, okay, fine, look at root. F of root is going to be S, and here whatever tree I get, I make root S and I try this second attempt. Now I am taking this graph S, this, because now I know that, but is this helpful? Still is it helpful? Because yes, I gave S to him, but I never forced that the neighbors of S is here, right? I could still, I do not know what you are storing at T1, it may store some vertices of S, it may not store some vertices of S. So when I still do this, I could still get a neighbors of this. So this is, look at here, look at here, right? What I want, I would like Vi, I would like an independent set here which doesn't contains, which independent set which does not contain any neighbors of x. But look at this function which associate at R1 some set of vertices. I still have not forced him that all the neighbors of x is contained here so that I can just copy the solution which contains here. I still cannot do that job. right? I can still not do that job because I have not forced anything S to have. Okay, so this is actually not going to work like this. Like, so this graph is okay because now at least these edges are being considered. So this is beautiful. But here I could do a something more, is that I force you that look, I don't know what you are going to do, but in Ri, S must be subset of f of Ri for all. Now let's see if I force this, then what happens? Look, I'm just trying to fix my decomposition. I'm not doing anything. I'm just trying to fix my decomposition, which will allow me to do my dp for independent set. What happens if I force S should be a subset of f of Ri? Or think of this way, let's go back to the previous decomposition. Okay, let's go back to the first decomposition we made. We made S, we made decomposition which basically separated, then another separator, separator. So this itself is giving you a tree, right? Separator, 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 suppose, right? The connected component, and then I find another separator, then their connected component finds, and this is partition. Suppose, here's a one quick fix. What I do, pass S to all its descendant. So pass every subset. So like, what is your bag? Currently your bag is this, this, this. Now what I'm going to do, I'm going to make this guy included in all the bags below him. And I do this for everybody. So suppose the depth is D, the size of this object could be as bad as D times T. Like, because you have added this T size subset to everybody, right? This also to everybody, this to everybody. So the last guy will get subset from everybody. So it could be, the sizes could be as bad as dt. So if D is not too large, maybe still we are very happy. But is this okay decomposition? Let's try to ask this question. Maybe it has blown up my bag very much, but can I now do my dp? Okay, so you fix a subset here, okay, right? What I want, so I want an independent set which contains what? Not its neighbors, right? So this is all that I wanted. I wanted my independent set to contain this guy, but not. But if I look back here, but I have something. What do I have here now? I have the whole set. Is that enough? Huh? So if I look at the corresponding guy here, what does it tell? Give me something from below, like independent set from below, whose intersection with this bag is precisely this. This is all that is saying, right? But it still doesn't tell me that I cannot contain a neighborhood of him. From here, look, all I know that S is here.
So now you have whatever black set you have in the top root bag. In this bag, the intersection S, if it is that same, then whatever independent set you have from below,
Yes.
that has to be independent with this.
So what does that mean? Now I can do? So now I can do. Are you sure I can do?
The same thing won't hold. You need to ensure that you keep X.
What? X is independent by definition. Otherwise, I stored something garbage there. That I can check in the beginning itself. That's okay.
Like if you say that is S, so S minus X must also not be there. So here we need to do some modification to this. F of Vi minus N of X minus S minus X. in this node we want exactly X, we don't want the others. So
Okay.
we need to ensure that that is also not there. So when
Yeah, so okay, so you are right. I should maybe check f of vi minus nx minus f of v minus x. Is that what you are saying? Okay, fine, add it. Because you don't want those two also, right? But can this independent set contain neighbors of x? That's my question. Suppose I did this, can this independent set contains neighbors of x? No? Why?
because when you go down
So,
The subgroup has to find an independent set in the subgroup.
yes, I,
This is part of every node.
yes,
so any independent set that we are forcing X in will not have X.
yes, because everywhere I have put s inside. But what is the problem with this decomposition? I mean, it could be as bad as n for all that I care, so this is not good enough. But this is helpful, okay, right? So we will try to get this decomposition, but we will be even more smarter than here, okay? So what will I try to do? Excellent is that what made it work, because S was somehow everywhere. Now the problem is that I force S here and another separator here. Maybe I don't want to force S everywhere, but maybe portion of S here and portion of S here. You get my point? Look, I will add S here, but imagine that S got distributed half the vertex in this component and half the vertex in this component, then actually you are not adding whole of S to everybody, no? Imagine yourself that S got distributed, so like 10, so S I have to add here, I have absolutely no choice. But suppose when I found a separator which also separated S nicely, then I am doing a great job for myself, no? Because then, okay, find S by 2 vertices here, S by 2 vertices here, right? So maybe the contribution of S as I go down is decreasing, which is perfectly fine. So I am not interested in any separator, but I also want a separator which separates S, okay? So let us write it down. So what do I need? So we need separator that separates S, okay? Okay. So now we will go back to the trees. I mean, because what is this setting? The setting is you are given a graph G, let us say a tree T and W, okay, and I am asking, does there exist a vertex V in T such that for every connected component C of T minus V, what do we have? C intersection W is less than equal to W by 2. I do not care how big your connected component is, but I want W to be distributed nicely. Up until now I was talking about a balance separated with respect to size of T. I said no, I gave you a prescribed set, can you shatter it? Okay? Okay. Okay. So now let us say, let G be a graph and let G be a graph, W be a subset of vertices and S be a subset of vertices. S is called balance separator with respect to W if all connected components of G minus S has the property that C intersection W is at most W over 2, right? So it is a separated with respect to W, not with respect to whole vertex set. You gave me a W and you want me to separate it, I'll give you a vertex. Okay, okay, okay. So now we'll go back to the trees and try to fix things. Okay. Okay. So what did we prove yesterday? So this is a theorem which we proved yesterday. Every tree T has a vertex V such that every connected component of T minus V has size at most Vt by 2. Okay. I want to prove a slightly different version now, which I call weighted version. Okay. So now I also have a tree T and I have a weight on Vt. Okay. Okay. Want to find a vertex V such that for any connected component C of T minus V, we have that weight of C is less than or equal to weight of T divided by 2. Suppose I prove this, then I can prove this very easily. Why? That is very easy. If I prove this, then I can prove this lemma very easily. What function, weight function I will define? Okay, you define a weight function from vertex T to 0, 1. Okay, for all W in W, weight of W is 1 and 0 otherwise. Right? So this is the only guy who has a mass, right? So look at any C intersection W, it has to be the total weight divided by something, so it is W by 2 because that is the total weight. So if I prove this, I am done. And haven't we proved this? I mean, we apply the same argument, right? Okay, here is a vertex V. Why is this not doing the tree? Look at all the tree, there exists which is heavy. And so the weight of every other tree is strictly less than weight of T by 2. Okay, so move the token to the next one here, the heavy guy. Does B component and everything else is weight smaller. Keep doing it finite step so we can achieve. This is exactly the same proof, it's just that, so tree had actually much better property. Okay. So now I am going to change my definition of T decomposable graph. Okay. How did I define the notion of T decomposable graph? I defined the notion of T decomposable graph to mimic the property of separators. Okay. Now I want to mimic the property of the new separation which I need for my issue. Okay. Let me see where I have reached. Okay. So here is my definition. This is why I did not. Okay. A graph G is T decomposable. Okay. If for every H subset of Vg, W subset of H, okay, okay, there exists a set S of size at most T, okay, then there exists, let's say, there exists a W balanced, there exists a W balanced separator of size D. Means you are given an H and you are given some W, okay, and what is our goal? Our goal will be that, okay, fine, I will find you a separator S, so that if you look at any connected component, W is distributed evenly, like that, like W is not unbalanced, W is balancedly divided among its connected components. So this is my new definition of T decomposable graph, right. Clearly zeta 1 contains forests, okay, I do not know what zeta 2 contains, okay. So now we will, so now let us try to do a natural strategy now that we have such powerful object. For this, what will I do? Okay, this is still a goal. So what I would like to try to do is that, okay, fine, I find an S, it separates, okay, I will say wait, I want, look, as I told you, right, the way we were doing DP, we wanted the tree here to contain S in its root, that is important, right. So we should make our induction assumption stronger, right, because we will compute anyway things in like inductively. If the number of vertices is too large, we will do something, okay. Okay, so first of all, what we like, okay, the tree that results from induction has in its root what? S. This is like I want it, okay, very good. So now you are looking for a decomposition which is basically Ci S union Ci. So like for this I will give a decomposition, okay, for this I will get a decomposition, and what is the property? Additional property that it has size, it contains S, and I will add S and make him this. So I will put it f of r equal to S, and then the way we were doing just this, okay. But what we will do next is something very different. So here to apply this induction, I will give him set W and say split him, okay. So what will happen, I am not going to call him like this, I am going to call him, look, this Ci has a balance separator, this Ci has a balance separator, right, but I will not call him like this, I will say, okay, look at Gi, which is graph induced on S union Ci, I also give you a set S, okay, and something here. So next time when you have to find a separator, it must be separating S. I am not interested in any separator, but I am interested in separator which also makes S balance, right. So it is okay that S is contained here, it is okay that S is contained here, but in the rest, because S has bifurcated, you only keep portion of S here, portion of S here, portion of S here, right. Now why am I doing this? Ultimately I want the sizes to not blow up, like this, the number of vertices which I am associating with this function does not blow up, right. So what we will try to show that it actually, look, what is the property? There exists a T sized separator, right, which does all this job, right. So I can come up with a decomposition of F where I will tell you that, so what is my goal? My goal is ultimately to come up with 2 to the power Vg, okay, where all I wanted to oh, if S is there, then it is everywhere kind of property to propagate, and I did not want them to big, then I said, hey, if I separate him, then this side, this portion of S is not there itself. What is the point of adding whole of S to this guy, because they are not even present in this graph. So wherever they are present, you add them to there, right? So that is the kind, so like not everything is being distributed, but whichever goes to whichever component goes and sees everybody, right? Excellent. Such that for any V in Vt, okay, f of V is upper bounded by some alpha t, okay, where alpha will be like some 4 5 constant, okay, and then we will see what is a, then we will see can we do our independent set algorithm with this, and then we will extract out what this kind of decomposition means and what is the name of it and blah 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 and everything at 4:30. Okay, I think we have reached where we should stop.